Now we'll look at I'll talk about this one. Two competing headache remedies claim to give fast-acting relief. An experiment was performed to compare the mean lengths of time required for probably absorption of brand A and brand B. 12 people were randomly selected to give an oral dosage of brand A. Another 12 were randomly selected to give brand B. Lengths of time was recorded. The mean standard deviations and size of the two samples are below. Past experience with drug consumption permits that researchers assume that both distributions are approximately normal, so we'll need that. Let's use a 5% level of significance to test the claim there's no difference between the two brands. Also find the estimate for the p-value and the sample test statistic. All right, let's get into this. First, they're gonna ask you what the level of significance is. So I know this is pretty simple, but you need to. So level of significance 0.05. It's just this is a decimal. Now the next, we've got two means, two independent samples, and we're trying to test their difference here. So this is called a difference of means. So our null hypothesis, we're going to assume that mu1 is equal to mu2. We assume the means are equal. And let's look at what we're trying to prove here. Let's read the context. Test the claim there's no difference between the two brands. So we're testing the claim there's no difference. So what are we trying to do? We're trying to find that there is a difference. So equal to slash through it. You might have to put exclamation point equals on your WebAssign. Now the question is, what distribution are we using this time? I haven't got into this. I'm kind of teaching as I go. The question I'll ask you is, are the standard deviations known? The population standard deviations? No. We don't know sigma 1 and sigma 2. We know S1 and S2. Those are the sample standard deviations. So we know S instead of sigma. We're going to use the student's T distribution. T distribution. So we're using the student's T distribution. And when we do this, we assume that both population distributions are approximately normal. Now, here's the thing with unknown standard deviations. Unknown. So we don't know the population standard deviations. You could say sigma 1 and sigma 2 unknown. So we don't know the population standard deviations. We don't know sigma 1 and sigma 2. So we have to use the T distribution. Okay? So we have to use the T, and we have two samples. So what are we going to use? We're going to do a two-sample t-test. You can also do this in SALT. We're going to do a two-sample t-test. We can go to stat, test, two-samp t-test. So stat, test, two-samp t-test. Okay. We'll t-test. We've got the stats here. So X bar 1 is 21.8. So it's pretty simple. Once you identify the test, it's pretty simple. It just tells you what to do. SX1 is 8.7. N1 is 12. X bar 2 is 18.9. S of X2 is 7.5. And then N2 is 12. And it's not equal to, we put no for pooled. Okay, that's a whole other issue we have to talk about. That's an issue telling if the variances are the same or not and all that. We're not getting into that. So no for pooled, no pooled. And I'm just going to do draw. I like doing the draw because I could see the curve. I meant to delete those earlier. I apologize. So on this one, I'll draw a curve here. And on this curve, it's going to be two-tailed again because it's not equal to. So we're going to have two tails shaded. Okay? We got two tails shaded. And our Z value, or our T value, I apologize, T value, that's important. This is our test statistic. I'm going to erase this. So our test statistic is T. That's 0.875. They usually go 3 spots on T. The p-value is 0.3915. So how does p-value compare to alpha? P-value, is it greater than alpha or less than alpha? Greater than. When p is greater than alpha, we fail to reject. When it's less than alpha, we reject. So we failed to reject Ho. Okay, so we failed to reject Ho. And so that means not statistically significant. Not statistically significant. So what does that mean? You'll make your claim. This would be their last statement. We failed to reject Ho. We failed to reject null hypothesis. And we have failed to reject Ho is like not guilty. We have insufficient evidence to suggest or to say that there's no difference, that there's a difference between the two brands. That there is a difference between the two brands in mean time for bodily absorption. And you don't have to write it. I'm just trying to kind of basically, you'll kind of see on your paper. I'm going to pause there. Okay. Now, this part, as I said, it's by hand. It's completely optional. I'm just showing you how to do it by hand. You don't have to know this. Okay, you could use salt today on this. But by hand, we find the T, and I have this looks like I have this written wrong here, or no, this over here. Okay, so T equals, here's the formula for T. T equals the statistic in this case. It's similar to the Z one. It's the difference of the means minus the difference in the sample means, I should say, minus the difference in the hypothesized means. So they call this statistic minus parameter divided by the standard error, which is just the standard deviation, this is actually very similar to the last one. It's just you have S instead of, and we'll have a little difference here when we're doing the p-value. So that's your test statistic. So x bar 1 minus x bar 2, that would be 21.8 minus 18.9 minus the difference in the means here, the hypothesized difference. Well, that goes back to Ho. What are we assuming the difference is between the two means? We're assuming there's no difference. So this, once again, this is just going to be 0 because we're assuming there's no difference. So the difference between the hypothesized means would be 0 divided by the standard, the square root of S1 to be 8.7 squared divided by N1, which is 12, plus 7.5 squared divided by 12. That's how you do the T. So it's going to kind of look similar to the 21.8 minus 18.9 divided by the square root of 8.7 squared divided by 12 plus 7.5 squared divided by 12. Okay, that should work. 0.874, okay, 0.874, and that is pretty accurate there. Okay, looking at the 0.87, actually 0.875, I apologize, didn't round right, so that's accurate. So this is going to be 0.875. Now this is where it might get a little off track, is now we've got to calculate the p-value. So I'm going to draw out this curve. Zero's in the middle, and so 0.875 is above here. But the problem is it's a two-tailed test because it's not equal to. So this one's got two tails. So I've also got a negative part. So I got to do the negative of that, and I'm going to be shading both tails. Now, when it's a Z, we use normal CDF. When it's a T, we use something called TCDF. We're going to use TCDF. I'm going to do TCDF for one tail. So I'm going to do TCDF for that tail. My lower bound's 0.875. My upper bound, I just make up a large number because it's going on forever. Now, they'll also ask for degrees of freedom. In this one now, this is where it varies. The real degrees of freedom formula is a very long, complicated formula that we don't want to do. So what they do for this one is, if you're doing it by hand, you take the smaller n minus 1. So I look at both samples and I say, if I do n minus 1 for each sample, which one would be smaller? What's 12 minus 1? 11. What's 12 minus 1? 11. So which one's smaller? Well, they're both the same. They're both 11. This is going to cause my answer to be a little different from my original answer, and the original one's actually more accurate. So because it said the real degrees of freedom formula for this is very complicated. And then whatever I do with this, remember I got to multiply by 2. So 0.200 now times this by 2. 0.2001. Okay. So 0.2001 and then 0.2001 times 2 because there's 2 tails. 0.4002. So it's a little different from that one, but it's relatively close. And that's because of degrees of freedom. We're not using the real degrees of freedom. We're using an estimate. So that's how you do this by hand.